Alright, now this last video is typically going to give you an idea of how these graphs or these rational functions behave around the asymptotes. More like how you behave really around your crush. So you're going to say this. Imagine you have one vertical asymptote and one horizontal asymptote. Yeah. Now, and notice that you're going to have four portions in which you can graph your graph. So you have one, you have two, you have three, and then you have four there. Now, how do you know which of these your graph will be in? Will your graph be in all the four? Will your graph be in one? Will your graph be in three? Will your graph be in two? How do you know? So the first thing that you must know is that when you've been given, if your asymptotes have been represented in such a manner, or if you have found asymptotes that present themselves in such an orientation, your graph will always be in two regions. Okay, graph will always be in two regions. Now, how do you find these two regions? These two regions, first of all, you must know that they lie diagonally. Okay, so if you found that your graph must be in region 1, your graph must be in region 1. Therefore, your other graph is going to be in region 3. They usually go, they have a diagonal behavior. So if you found that your graph is going to be in region 2, meaning your other graph is going to be in region 4. That's how it is. It's rare when you find this to this. Rare to closely impossible. So always go with the diagonal part. So if you just find to say, okay, my graph lies in portion 1, meaning the other graph should be in portion 3. Good. Now, how do you have an idea on which specific portion your graph will be in? The best and easiest method is to pick a number greater or lesser than your vertical asymptote. Okay, so imagine your vertical asymptote here is like a 2, yeah, and then you had something that said maybe f of x is equal to what? F of x is equal to maybe yeah 2, something like that, and then we say no, it can't be 2. Maybe let's say x plus 1 over what? X plus 1 over x minus 2. Yeah, perfect. So in this case, maybe, meaning your horizontal asymptote is going to be a 1, right? Because if you get the coefficients of x at the top and at the bottom, you should have a 1 there. And then setting this equal to 0, you must have a positive 2, which is that positive 2 there. Good. Now, how do you know? So you can either pick a number greater or lesser than the vertical asymptote. So the best is to pick a number less than the vertical asymptote here. And the number that you can pick is simply 0. So you're going to find your f of 0, which is going to be 0 plus 1 over 0 minus 2. So notice that you're going to have with a 1 over negative 2, right? Meaning this 1 over negative 2 is in the y region, right? So somewhere below there. So this would be like how? Let me just get rid of that there. So we had what? We had negative 1 over 2. So negative 1 over 2 will be here. So negative 1 over 2 is in portion 4, meaning that my graph should lie in this portion like this. And not forgetting that our graphs always go towards the asymptote, but they never touch across it like that. Okay, and knowing the diagonal behavior of these guys, so if my graph is in region 4, meaning it should be in region 2 like that. Yeah, then that is how I know. Yeah, so we can also have another orientation where, let's say this is your xy plane. Now this time let's have two vertical asymptotes, a vertical asymptote there and a vertical asymptote there. So this usually comes about when your denominator is more of a quadratic expression and then you find two values of x. Yeah, and then let's say we have one horizontal asymptote like that. Yeah, now in this case your portions have multiplied themselves. Yeah, they have multiplied. So we have how many? We have 1, we have a 2, we have a 3, we have a 4, we have a 5, we have 6. So the things that are separating these portions are the asymptotes. Okay, so we have region 1, 2, 3, 4, 5, and 6 regions here. Now where exactly does your graph lie? Where does it lie? Cool. So to know that, again, you would have to pick a number either greater than or lesser than any of your asymptotes. Yeah. So let's say here the best would pick. So let's say here we have a positive 2, then here we have a negative 2, Yeah, positive 2 and the negative 2. And then let's say this is what? Let's say this is negative negative 3, right? So coming up with our function, maybe the function would have been your f of x is equal to what? It is equal to this like that, and then we're going to have something that says what? We're going to have something that says negative 6, negative 6x plus that, and then this is over what? This is over 2x squared minus something something. Yeah. So whatever this is. So this is not the actual function. I'm just assuming this was the actual function. So what I would do here is this. So let me just get rid of the squared like that. Yeah. So what I would do here is this. I would pick where x is equal to 0. Yeah. So replacing there with 0, I would have what? 0 over negative 2, and it will give me what? 0. Therefore, I know 0 is in the second portion over there. So I know my graph would, touch something like this. Let me use a different color. I know my graph would come from here, touch that part there, and then it goes back there. Now, knowing that graphs have diagonal behavior around asymptotes, it's like how maybe this might be a road, right? This might be a road. You're walking here, your crush is walking here. You get too nervous, so you try to change your road going diagonally while your crush pushes right straight there. So this is how these asymptotes can be represented. So you have your graph like that, and then diagonally you would either have this region or this region. So this would either be region 4 or region 6. So your graphs would either come from there like that, or it would come from there like that. Knowing again that your graphs are sort of attracted to your asymptotes, but they never touch the asymptote, they just run parallel to it. Yeah, so that is how it would be. So just in case maybe your graph came out here, meaning that it would come out from here and from there like that. Yeah. And the last most complicated situation is where you have an oblique asymptote that is maybe a quadratic expression. For example, your oblique asymptote comes out like this. This is your oblique asymptote. And then you have vertical asymptote that's somehow there as well. Now, how many regions do you have? Here you have the following regions. You have region 1, which is this entire space, region 2, region 3, and region 4 there. So where does your graph lie? You'd either pick a number greater or lesser than your vertical asymptote here. Yeah. So if this is maybe positive, if this here is maybe positive 5, and then you find that after you place in a number that is less than your vertical asymptote, let's assume your vertical asymptote was like a 2, so you pick a number that is less than 2, and then you find that the answer that you found is let's say here you pick 0, and then you say after you pick 0 you plug it into your rational function, you get a number that is greater than 5, maybe let's say 7, meaning that your graph must come out of that portion there. Right? So how you graph that? Meaning that the diagonal behavior, if one graph comes out of this region here, meaning the other one will come out of this region here, right? Because they never really go straight like that. It's diagonal, so it would come out here. So keeping in mind that your graphs are attracted to your asymptotes, it would come like this, and then it goes like that, and then this other one would come from there, and it goes like that, and it goes like that. Yeah, so that is the behavior. So you can have another scenario where you have something like this and this. You have something like this, and then you have something like this as well. So after you plug in something that is less or greater than your vertical asymptote, you might find that your graph lies in this portion 1 and this portion 2. So your graph would be like how it would come like this and like that, and then it would also come like this and like that. Pretty funny, right? Yeah, but that's the gospel truth. So yeah, good luck.